Very good morning. Today we are dealing with that is transmission lines and RF system design. In that we have a special topic coming under transmission lines for high frequency signals. In that the topic is measurement of VSWR and wavelength. So before going to that, we should know what is this being the very important topic. We should know what is VSWR and why is it needed to measure it, and what are the methods available. So once mostly the three important methods are being available, we will see it one by one. So VSWR is the called as and the magnitude of voltage reflection coefficient are very important parameters which determine the degree of impedance matching. So whenever we have you can imagine a transmission line, it is a pair of wires through which the signal is being getting transferred. The transmission line it can be of any length, that is it can be of a kilometer length. For example, if we cannot make a transmission line of whole length at one stretch, with the transmission line will maybe a parts, so it will be splitted into parts depending upon the manufacturing process. And when the signal is getting transferred from one place to another place, that is from one part of the transmission line to another part of the transmission line, the signal will be proceeded to the next stage only if its exact impedance is matching with exactly. That is, if the impedance is not matching, the impedance of the two signals when it is being transferred from one part to the another part is not matching, the signal may get reflected back. It cannot proceed further. So that is called as impedance matching. So when the impedance matches, the signal will be transferred to the next part of the transmission line without any disturbance. We need to measure that where the impedance matching occurs, is the impedance matching is proper. So that and all is being done by measuring the parameter like that, that is reflection coefficient and voltage standing wave ratio. The voltage standing wave ratio is the one where the waveform is getting reflected to the original signal. If the impedance is not being properly matched, then what happens? The signal may get reflected back. So the signal cannot proceed further. So the waveform is called a standing wave. The wave is called a standing wave. And the voltage at which it occurs, or the point at which it occurs, that measurement point is called as voltage standing wave ratio. So the voltage standing wave ratio is being determined by the value of Vmax by Vmin, where the standing wave occurs and its maximum amplitude to the minimum amplitude. It can also be represented by means of the reflection coefficient. Since the standing wave is only because of the reflected wave, it can also be measured by terms of the reflection coefficient. We'll see the formula in the next slide. The first slide is related to measurement of VSWR. So how we can measure that voltage standing wave ratio, because it is being important to determine the degree of impedance matching. This VSWR and reflection coefficient are also used for measurement of load impedance by the slotted line method. So that slotted line method is being shown here. You can just see that the first one is the microwave power supply, where the signals are being generated. Microwave source where the signal is being generated, and that source needs a power supply, that is microwave power supply. And second one is the isolator. From the external signals we need to isolate, we need to isolate the signal, and the signal has to go to the next stages. And we have the frequency meter for measuring the frequencies, and we have a variable attenuator whose attenuation can be varied, and we have a slotted line. So slotted line, you can imagine where we can external parts can be at any instant can be added, and some measurement can be done and can again be removed. We have a provision in between of transmission line. We have a slotted line section. So the slotted line section, we have a tunable probe detector to detect that VSWR measurement through the tunable probe. We can measure that, and to detect that is being determined. The value is being determined by the VSWR meter. And we have an unknown impedance and matched load. That is unknown impedance can be measured by means of the probe VSWR meter. Shows that where the slotted line, where the standing wave occurs and its maximum value and minimum value. Based on that value, we can just measure the impedance values, and to provide a better matching, that is to provide the impedance matching, we can find out the matched load. So this is what the diagram of VSWR measurement. And after measuring, that is when the load impedance is not equal to the input impedance in the transmission line, then the standing wave is produced. That is, then the reflection takes place. We told in the beginning point, that is, if impedance is not being properly matched, then the waveform get reflected. Those impedances called as the load impedance and the input impedance. If it is not being properly matched, then the waveform gets reflected back. So the VSWR can be measured by detecting the Vmax and Vmin in the VSWR meter. So you can just see the standing wave ratio, that through the probe we can detect the that Vmax value and Vmin value by just moving that through the slotted line section. And that after the measurement, that VSWR meter shows the reading of Vmax and Vmin. So once we measure the Vmax and Vmin value, we can measure the standing wave ratio. The standing wave ratio equal to Vmax by Vmin, which is equal to 1 plus the reflection coefficient by 1 minus reflection coefficient. The reflection coefficient is the number of, that is the power of the wave reflected divided by the instant wave. That VSWR can be termed as a low value if the standing wave ratio is less than 20, being measurable, that is being common to importance when it is being greater than 20. And how to calculate the reflection coefficient is the ratio of electrical field strength of the reflected and incident wave are called as reflection coefficient. I can just measure it by means of the formulas. That is E reflected to the E incident. So it can also be equated to your impedance values. So Z is the impedance at the input point and Z0 is the characteristic impedance. So Z minus Z0 by Z plus Z0. We have a different derivation for the reflection coefficient. Based on the derivation, we have the formula Z minus Z0 by Z plus Z0. Z is the input impedance, Z0 is the characteristic impedance. So from the above equation, we can determine the reflection coefficient. Reflection coefficient, it just gives the following equation, that is S minus 1 by S plus 1, because S is the VSWR parameter and S is the VSWR reading. It can be represented as Vmax by Vmin, and if we get two equations, that is Vmax by Vmin, in terms of a reflection coefficient, if we are writing it, we can just follow the previous formula, that is 1 plus reflection coefficient by 1 minus reflection coefficient as Vmax by Vmin. So if we simplify this equation, we get reflection coefficient in terms of VSWR. That is VSWR is S minus 1 in terms of S, if we are representing it, it is equal to S minus 1 by S plus 1. And we have a graph for this double minima method. The same setup, we can just measure the Vmax value and Vmin value, and we can put it in a graph. The minimum point occurs twice the time, and where the maximum point is only 1 point, and the two minimum points we can take it as x1 and x2. X minimum is x min, and for the values we take the 3 dB lines, we can extend it to the lower line. So through the graph we have some set of thing. So this another method is VSWR can also be denoted by Emax by Emin. We know that that is Vmax by Vmin also we can write. So this E max is nothing but it depends upon the value of incident wave plus the reflected wave, and E min is nothing but incident wave minus the reflected wave. So E max by E min can be represented as incident wave plus reflected wave by incident wave minus reflected wave. So the power is directly being proportional to V square by R. So that can be termed as P min, and for the values of V min, and for the values of V max we can take it as P max. So 2 times of P min equal to proportional to Vx square. So that is P min is proportional to V min square, and P max proportional to Vx square. 2 times of P min equal to Vx square. So that can be represented as Vx equal to root of 2 times of V min. Root mean square value we can take. So the guide wavelength, by moving the probe between the two successive minima and distance equal to that lambda g by 2 is found to determine the guide wavelength. So the transmission line distances can be of 3 types, that is, one is at lambda by 4, and another one at lambda by 2, and another one at 3 lambda by 4 and 5 lambda by 4, like that. It goes on at a length of quarter wavelength, we call it. So based on the length, we have the wavelength measurement by using the formula lambda naught by root of 1 minus lambda naught by lambda c the whole square. And this is about the wavelength formula. So in this slide, in this presentation, we studied how the VSWR is being measured, and based on the VSWR measurement, we can find the reflection coefficient also by using the 2 different formulas, and how it get related to the wavelength. Thank you.